Hi everyone, welcome back to Chem Help ASAP. In this video, we're talking about kinetics, and specifically, we're going to be talking about first order rate laws. Let's get started. Before we jump into the actual rate law, I do want to do a quick explanation as to where this rate law comes from. So if we take a generic reaction A to B, here is our general rate law. This is also called the differential rate law. Now, when we're talking about a first order reaction, N is going to equal 1. So we can simplify our rate law to this right here. And in this form, it is ready to integrate. So once we integrate this form here, this is our integrated first order rate law. Let me specify this on the slide. What we call our rate law is actually a differential rate law. And our first order rate law down here, this is an integrated rate law. Notice for our differential rate law, we equate rate with concentration. But with our integrated rate law, we're going to equate rate with time. So this is the advantage of an integrated rate law. Let's take this rate law and I'm going to rearrange it so we get it into the y equals mx plus b form. And I'll show you what I mean by this. So here is my integrated rate law. Again, you notice I've just rearranged it here. I've just moved terms around. But the advantage of putting it in this form is it puts it in a linear equation form. So remember, an equation of a line generally is y equals mx plus b, where your y and your x are your variables. So this is what you'd plot on your graph. Your m is your slope and your b is your y-intercept. So let's see how these relate to our first order rate law. For our first order rate law, our y is going to be our natural log of a. You can see that right here. So this means if you are making a linear plot, your y variable needs to be the natural log of the concentration of A. Now, what about slope? Slope is going to equal the negative value of K. Well, remember, what is K? K is your rate constant. This is unique for every reaction. Finally, your B or your y-intercept is simply going to be the natural log of your initial concentration of A. So let's see how we put this into practice with an example. Okay, so I've got a reaction up here of dinitrogen oxide going to nitrogen and oxygen gas. So what I'm going to do is I'm just going to monitor concentration of dinitrogen oxide according to time. So you can see I have concentrations, I have times. But I want to know, what is my rate constant for this reaction? I also do not have my initial concentration. What was my initial concentration of dinitrogen oxide at time equals 0? All of these can be calculated once I get my linear plot. Well, I have my x values right here. My x is going to be time, but my y values are not simply concentration. Remember, my y values must be the natural log of concentration. So you can see I have now this third column where I've calculated just the natural log of my concentration. Now don't worry, I know these values seem a little bit off, but it will form a linear plot. So plotting my natural log of concentration versus time gives me this plot right here. You can see I'm very nice and linear. And I've also displayed on the graph my equation of the line. So you get this equation of a line by doing a linear regression. Now, usually most calculators will do this for you, or if you're working in something like Excel, Excel will also calculate this for you. This gives me my slope, and this gives me my y-intercept. Okay, so I wanted to know the rate constant for this equation. Well, remember, my slope is simply my negative rate constant, so my rate constant is just 0.0694. What about my initial concentration of dinitrogen oxide? Well, remember, your intercept is just the natural log of your initial concentration. That value, of course, is 0.0004, which means my initial concentration of dinitrogen oxide is 1 molar. So just knowing the equation of the line gets me both of these values very, very easily. Okay, well, let's do a different kind of problem with this data. What if we wanted to calculate the concentration of dinitrogen oxide at 25 seconds? Let's pull out our first order rate law. Here it is right here. I'm looking to calculate a concentration at a certain time. So I'm looking to calculate this concentration right here. I know my initial concentration. I just calculated it up here. I know my K because I got that from my slope. And I know how much time is going to elapse because the problem told me 25 seconds is going to elapse. The one thing I do want to check in terms of my time is that my time is measured in the same units in my problem as in my graph. And yes, you can see my time is measured in seconds in my graph and seconds in my problem. So if this was 25 minutes down here, I would need to convert that into seconds because I'm monitoring in seconds up here. So all I need to do is just plug in everything I know, and I'm going to solve for this concentration at 25 seconds. Okay, here we go. So my natural log of A, which in this case is just my dinitrogen oxide, stays the same. That's what I'm solving for. Minus my natural log of 1 molar equals my negative, my slope, and here is my 25 seconds. That's my time. I'm simplifying this right here. And this gives me my concentration at 25 seconds is 0.176. Does this make sense? Well, let's go back to our data. 25 seconds is going to be in between 20 seconds and 30 seconds. So my concentration ought to be somewhere in between 0.250 and 0.125. And yes, it exactly is. It's in between these two concentrations. I hope you found this video helpful, and thanks so much for watching.